Hello, I'm going to talk more about the solenoid and how you get a magnetic field from a solenoid. Remember what a solenoid is. It's basically coils of wire wound around something, sort of like this. And if even just a couple coils of wire would create some sort of a solenoid, but they typically have maybe hundreds of coils. So a slinky is a good example of a solenoid, and that is what you'll be using in lab on Tuesday. Now, if you remember, if you have a current going through a wire from one of the previous videos, you can look at the magnetic field, you can visualize it as if you put your thumb in the direction of the current, the lines of the magnetic field actually wrap around the wire, forming circles, closed circles around the wire, is how the magnetic field lines are created. Now let's just say the wire was in a loop, single loop like this, with the current going this way. If I put my thumb in the direction of the current, the magnetic fields all around the wire are going to be pointed this way. They're going to wrap around this loop and then come back again. So they'll look like this. If I could show them all, there'd be, an infinite number of loops around the wire like this, but each one separately closed. Now, if I did two of these wire loops, you can imagine that each one of these loops is going to have its own magnetic field because of the current passing through it. It's the same current, but it's a distinct loop. So each loop is going to make its own contribution in the magnetic field. So for instance, the current here is going to create the one we just saw, and then the current in the next loop is going to create another one like the one we just saw. So through the center of the loop, the magnetic field is going to reinforce from each of these separate loops put together. So the sum total of this in a solenoid, if you have 100 loops, you can imagine the magnetic field in the center of all of these loops is going to be reinforced on the order of 100 times more than if you just had a single loop. And it's also going to have some width to it because you're going to have a number of loops together like this. They're going to form some, they're going to have some significant dimension in this along the length here. And also outside of the loop, out here, the magnetic field lines are much more dispersed. Magnetic field is essentially zero outside of the solenoid. But inside the solenoid, it's pretty strong. And inside the solenoid, it's actually also uniform. So this is actually the magnetic equivalent of the two plates for the electric field, where you had a uniform electric field. In the middle of a solenoid like this, you have a uniform magnetic field. The strength of that magnetic field is given by this equation right here, which says B, which is a magnetic field vector. The direction, of course, is, as we pointed out, it's through the loop, depending on what direction the current is, whether it's clockwise or counterclockwise. The direction of the magnetic field will either be going through the loop this way or through the loop that way. But the strength of it is going to be given by some other constant, which is called the permeability of free space, which is the magnetic equivalent of the permittivity of free space. It's given by the symbol mu0, multiplied by n, where n is the number of coils you have per length of meter of wire. So per meter of solenoid. So if your solenoid, if all your coils is 1 meter long, and if you have 100 loops in there, then n would be 100. If you have 100 loops and your coil was only a half meter long, then n would be 200, because in a 1 meter length, you'd have twice 100 loops. And then I is the current that's passing through the wire of all of these loops, and that would be in amperes. So the units in the end would be, B is in teslas, that's the units of the magnetic field, teslas. And you would get teslas by multiplying this constant mu0 times n, where n is the number of loops per meter, and I is the current in amperes. We'll talk a little bit more about units on Thursday, but I want to make sure that for lab you have at least seen this equation. Now what you're going to be doing in lab is you're going to be starting with very small currents, like 0 amps, and of course if you have 0 amps running through your coils, you should have 0 magnetic field. But because you'll have non-zero magnetic field, because the Earth's magnetic field will still be there, you're going to take that opportunity with 0 current running through your coils to zero your magnetic field sensor. any sensors in the vernier system you can zero. And you'll do that with zero current flowing through the wires. Then you'll slowly increase this current I right here. You make it go 0.1 amps, 0.2 amps, 0.3 amps, all the way to 1 amp. And then you'll measure how strong the magnetic field is each time. Now the idea here in your lab is going to be to actually measure mu0. So you're going to be doing this experiment with 3 different spacings of wire, basically 3 different values of this variable n, and for each one you'll be increasing the current through the wire. I think you have 3 different trials. You'll have one where you have a slinky is actually your solenoid. You'll spread out the coils of the slinky so they're more spread apart. So your n is going to be smaller because you'll have fewer loops of the slinky per meter of length of the slinky. Then you'll compress it a bit more, and then you'll compress it even more, and you'll see what happens to the magnetic field. I think you can imagine what should happen to it. It should get stronger as n gets bigger for a given current. When you have all of these data, you're going to then plot a graph of B versus I, and from the slope of the line on that graph, you'll see if you can deduce mu0, which again is the permeability of free space, and then the number for it is 4 pi times 10 to the minus 7th. So remember, pi is about 3.14, so 4 pi times 10 to the minus 7th is something like 1.2 or 1.3 times 10 to the minus 6th newtons per amp squared. And again, we'll talk more about the units on Thursday, but hopefully this gives you enough information that you'll be able to successfully complete the lab, along with the information that you receive from Dr. Kodka in lab class. Okay, enjoy the lab.